Hey everyone, thanks for joining. We're looking at example 7.3, and that deals with friction and how we calculate the force of friction. Now, we talked about today in class that the force of friction, in this case the force of kinetic friction, that is friction caused by an object that's actually moving, is a value that we call the coefficient of kinetic friction, and that's different for every single substance. Every single material has a different coefficient of kinetic friction times the normal force of that object n. So we take our normal force times this coefficient or this multiplier, and that gives us the value of the friction force, that is the force that's actually opposing the motion. So here we have a problem. We have a car that apparently it would seem broke or has a world record for the longest skid marks. I'm glad somebody took the time to do something as important as that. But we're showing right here that the longest skid marks in the world were 290 meters. That's like 3 football fields. That's ridiculous. But anyway, so we can write that down. We can write that our displacement is 290 meters. The only other thing that we're told is that the coefficient of friction of the road, or the kinetic friction, is 0, or was 0.6. Now remember, this doesn't have any units at all. It's just a value. It's just a multiplier, you might say, or it's a coefficient. The only other thing that we can at least implicitly figure out is the final velocity. We don't know the initial velocity. In fact, that's what we're trying to find. How fast was this car originally going to make that long of skid marks? But the final velocity, we can figure out, well, that's just 0. It comes to a rest. So that's all we know. And just having learned this equation, friction force is the coefficient of friction times the normal force, you would think we would need to know the normal force. But we actually don't. What we can do is we can start writing down what all the forces are equal to in this system, and then, similar to the problem that we did today in class with the Atwood machine, we can set two equations equal to each other. That probably doesn't make much sense explaining it, but I'll show you what I mean. So this is all we know in regards to the givens. What we can say, however, is this: that the net force, or the net, you might say, external force on the car, that is, you might say, that is slowing it down, that's bringing it to a stop, is really just the force of kinetic friction, just like we have above right here. But you're probably saying, well, great, yeah, we don't know the normal force because we don't know the mass of the car. That's true, but let's just write it down anyway. So that would be the coefficient of kinetic friction times the normal force n. Okay, and we'll just leave it like that. We don't have any value to plug in for n. What this is telling us is that the only force acting on this car to slow it down is friction. And that makes sense because brakes and tires work on the principle of friction to slow down your car. But this is the only force right here, the force of friction. However, we can also write, and this is for any object, we can also write that the net external force on an object or even a system is equal to ma, mass times its acceleration, right? I mean, that's that's the basic form of Newton's second law. Well, if we take this equation up at the top here, this equation for normal force, we can take this one step further. Because after all, what is a normal force? Well, the normal force of an object is the force that the road exerts up on it, or that the surface, you might say, exerts up on it. That is based on the weight force that the car exerts down the road, and that is mass times gravity. course, we don't know the mass, but we can write it in above here. We're saying this normal force is equal to mass times gravity. In this case, because the road is flat. So we can write it one step further by saying this is all the net force here is equal to the coefficient of kinetic friction times mass of car times gravity. See what we did? This is, oops, come on now. This is equal to that. We just showed down here, which is all equal to the net force acting on the car. And it also happens that the net force acting on the car is the mass of that car times the acceleration, or in this case, it would be a deceleration. But what this enables us to do is to set these two equal to one another. Really, what we want to find is the acceleration, so that we can solve for how fast the car was initially going. So let's set these equal to each other. Coefficient of kinetic friction times mg equals ma. That's what we just stated above right here. Now what's nice about this is that the masses go away. They're multiplied on both sides, so they can both basically drop out. So what we're left with is a pretty basic equation. We're saying that acceleration is equal to coefficient of kinetic friction times g. I hate when my pen does those little squiggly things. That's annoying. There we go. I'll erase it there. The acceleration, or like I said, in this case, it would be a deceleration acting on the car, is equal to the coefficient of kinetic friction times g. Or that would be, what is our coefficient? That's 0.6 times 9.81 meters per second squared, which gives us 5.9 meters per second squared. That's our acceleration. Now I'm going to just do a dotted line box around it because it's not our final answer. But that's huge in determining how fast this car was originally going. How fast was the car going? We now can figure this out because we now know the acceleration, which I said is actually a deceleration, but that's how fast it was. You might say that's the rate at which it was slowing down, 5.9 meters per second squared. So we have an acceleration. A is 5.9 meters per second squared. Can we now solve for the initial velocity? I think we can. After all, we know that v final squared equals v initial squared plus 2 times the acceleration times the displacement. We know everything there now with the exception of initial velocity. So we'll rearrange this to say that initial velocity squared would be vf squared minus 2a times the displacement. Take it one step further. And I'm running out of space here, I realize. Vf squared minus 2a displacement. And let's see if I can't just move this up a little bit here. Grab this. Yeah, move it up. There we go. Look at that. And I've got one more line worth of room here, which equals, what's v final? Well, that's easy. That's 0 minus 2 times 5. Oops. Should really probably say -5. It's a deceleration. 5.9 times, what's our displacement? That was 290, right? 290 meters. And I still forgot to put my minus sign in there. You would know, Here's my minus sign right there. You would know that you would have to make that 5.9 minus, because if we didn't, we would have the square root of a negative number, which you can't have, because this is a minus out front here. So what the minus 5.9 does essentially is it undoes that negative, and so we can do the square root. So that would be the square root of all that, 58 meters per second. That was our initial velocity, which is, I think I calculated it to be 130 miles per hour, so that was pretty darn fast. But that's the velocity that this car was going before it jammed on the brakes and slid for like 300 meters almost. So we did this without even having to know the mass, because these two statements are true. The external, or the net force, can be stated like this, and it can be stated like this. Set them equal to each other, and it can be easy to find the acceleration. That's example 7-3. I hope that helped, and I'll see you tomorrow in class. We'll talk a little bit more about friction. See you then.